the calm before the storm. Things aren't as they were before. You best start bracing. Did you think you could keep us out? Shut the gates, forget
Hello there.
us now. Tides are changing. Can you hear the sound? Can't stop us now. We're not back in town, know what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution. Can you hear the sound? Ground beneath your feet, with a whisper in the trees. Do you feel us watching? Hunger in our eyes, victories on our minds. It's our time to rise. Can you hear the sound? Can't stop us now. We're not back in town, know what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution. Can you hear the sound? Back in town, know what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution.
Can't you feel that we're all one and the same, one and the same? The heart that beats inside is the drum and the bass, the drum and the bass. It's more than a moment, more than a feeling, more than we know. It's more than a lifetime, when is the right time, where should we go? 'Cause we're stars, floating around trying to find who we are. Yeah, we're stars, floating around trying to find who we are. And every time you wonder why, just look in the sky, look in the sky. 'Cause we're stars, floating around trying to find who we are, trying to find who we are. 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 My heart skips a beat when you're looking my way, you're looking my way. 'Cause when we fall in love, we all run out of words to say. It's more than a moment, more than a feeling, more than we know. It's more than a lifetime, when is the right time, where should we go? 'Cause 'cause we're stars floating around trying to find who we are, trying to find who we are. Trying to find who we are. Trying to find who we are. Trying to find who we are.
Good evening and welcome everybody. This is Obi-Wan Pez for and Simplex Pachinko. That's my channel name. So we're going to be doing some math tonight. Reading through some papers and figuring out what on earth all these things say, because I sure as heck don't know all the time. And see what the modern state of mathematics is. I think we probably actually need to turn this down even further, which is very sad. Because it's already like at 20% or something ridiculous like that. So, hope everybody's having a good day. It was Monday, I realize, so gotta mitigate the possibility for having a good day when it is a Monday. Kids and I were walking around town, did some errands. Had all sorts of good little mini adventures. Gotta spend more time outside. The sunlight is only out for a very short number of hours, so we do have to get as much as is humanly possible. Oh shoot, I think I started too late to get down over here. Oh well. Alright. So, let's try. Take a look at this one right here. We got the density of primes in the eigensurface of the symmetric group S3. Prime number theorem asserts that the density of primes less than or equal to n is asymptotically equal to 1 over log of n. Density of prime triples in coprime triples in Z3 space is determined, in positive Z3 space, is determined to be 3 zeta of 3 over log n. Oh no. Whereas zeta is the Riemann zeta function. In this paper, we proved that the density of prime triples in coprime triple on surface S, where S is equal to the points that satisfy z0 squared minus z1 squared plus z2 squared minus z0 z2 equals 0, is greater than 3 zeta of 3 over log n, meaning that S meets primes more frequently. This surface is the eigensurface of the symmetric group S3 with respect to irreducible representation. Okay. Feel like we should be able to graph that. Let's see. I do not have Octave up at the moment, so let's go ahead and do that. Okay, so if we go with XYZ space, x is equal to, we want to show you how this works. So let's see, window capture, unlock, move up. There we go. So that will allow you all to see what it is that I'm typing in. Okay. Meat Machine Rex, good evening and welcome. Hope everything's going well for you. Rex dead on exposure. Oh no. Okay, so for X, I think it was specifically saying we wanted like, well that was Z positive. Z prime triples and coprime triples on surface S equals this stuff equals 0. It's greater than that. Okay, so Z1, Z2, Z3 belong to Z plus 3. It's said to be coprime or relatively prime if the greatest common divisor of Z0, Z1, Z2, indicated by GCD of Z, or Z sub I if we really wanted to go there, is equal to 1. Okay. A triple Z is called prime if it is coprime and at least one component of Z is prime. So therefore 388 and 506 are coprime. Slightly amusing given that 0 is going to be a part of this, but sure, why not? We'll let that go. Let's see. So let's go with octave is going to go from 0 to 10,000, oops, with a distance in between of 1. So this should be, X should be at the top, what, no, right there. Right over here in this column you should see, right now it just says hashtag answer. You should see like X is a 1 by 10,001 yeah, 1 by 10,001 vector called X. So we're going to do the same with Y and Z. We're going to get ads in the middle of our... whatever, I guess I should pay for it or something. Just saying. Okay, so we got X, Y, and Z, which are 1 by 10,001. Hey, famished. I know, right? Protective heat shrink boots. Woo! Okay, so we're going to create that, and then S is going to equal the surface. Kind of like get a right click here. No, it's just going to tell me that that's a legal. I hope. Surf XYZ. rows z must be the same length y, and columns z must be the same length as length x. Okay, help surf. Okay. Mesh grid. Yep, okay. I need to do that first. So. Surface mesh is plotted using shaded rectangles. Vertices of rectangles xy are typically the output of mesh grid over a 2D rectangular region of the xy plane. Plot a 3D surface mesh. Cool. Z determines the height above the plane of each vertex. Oh, right. I didn't... I just called all three numbers. I didn't actually do anything with it. Yeah, no, that's fair. Okay. Optionally, color of a surface can be specified independently of Z by supplying a color matrix C, right? Okay, so we want a 3D surface mesh. That mesh should be x equals 1, 2. Okay, so let's Man, I don't remember anything about doing this stuff. Z is the vector of gradients. Something like that. Okay, so, the way to do this, what we want to do is to create a surface that has the... We want to create a surface that has the... I mean, I guess it's we want it colored. Huh. Could do something ridiculous like just capital Z is equal to, and then pull what we got here. So this is still gotta talk about that from last week. Right, x squared minus y squared plus z squared minus yz equals 0. So we want a point to show up every place that that is true. Yeah, no. Yeah, too many arguments. Alright, we want MATLAB plot points. Right, we could use plot data points. 3D. How y'all doing? 3D, hang on, 3D scatter plot. Scatter 3. Awesome. Oh, God. Reject. From the United Kingdom. Just. Oh, God, why? Alright, so we want displays circles at locations specified by X, Y, Z. At specific coordinates specify these. Okay. So this is Pen. How's it going? This should pop up in a second. We're doing some MATLAB tonight, so definitely feel free to help out here. There it is.
I have a pen. I have an apple. Apple pen.
It's also going to be time for YouTube to flip out at this video for possibly having other audio in the background that it doesn't recognize, and or I guess it only matters if it actually recognizes it. I pulled a No Copyright Sounds playlist, but at the same time it's not written by No Copyright Sounds, so I was like, eh. Actually, that's not true. It's a No Copyright Sounds album. So, hopefully it should work. Almost done with Python. Nice. That's the other thing, is that we could do this in Python, and it would probably make it way easier. Yeah. You know what? It would probably be easier in Python. Boop. Just do it in Java. Okay. So everybody's going to hate this. Everything about my programming, everybody's going to hate. Like, pretty much guaranteed. Let's see. Go there. We want to not be on this particular project. We want to simplex. Oh wait. Right. These are the math research things that I've been doing. Alright, we want a new project. Does it take pen as input? But that would be center pen. Alright, let's see. So what do we want? We want this to be. Surface plot. Yeah, we're still doing this window. I want to look at... I want to look at the exponential idle stuff. Fine. Do that in a new window. Okay, so I've got numpy that I want to... Oh, that's main. Ooh. This is just a... Yeah, okay. It's just crap. Doesn't matter. Oh no. What have you done? No module... We've done this before. Install package numpy. It's already installed. It's on the other one. I hate it. Printed out the painting that you did of Reese. Aw, that's awesome. Good job, Rex. Okay. Now. We want to do that's not the same as the other one. It's gonna be wild, but sure, why not? X equals 0, y equals 0, z equals 0. Wow, x is less than... Let's just do 100 at first. Yes, asterisk. Okay, what is its problem here? Let's go with that and see where that's going. Indent expected. Okay. So we do want those eventually, but not just yet. So So how do we want to do this? Should I? This is the brute force method, but we could cycle all x's, y's, and z's. This will be an O cubed time, which means that it will take, 100 each is going to be 1,000,000 computations. So, like, it's not hard. The computer would do it in practically no time at all, but it's still kind of a pain. Okay. If x squared, oh, nope, to start there, but that's not true. Liar. Okay. X squared minus squared, x squared minus y squared, there we go. I know words. It's better. X squared minus squared plus z squared minus y squared plus z squared minus xz. Not yz, but you know what? It doesn't really matter all that much. Because they are symmetric. No, actually it does matter because y is negative, x is positive. Okay. Sure. We'll go with that. Right. Oh, I didn't want that window. I wanted P-charm. This over here. And put that over here. Cool. Right, plus z squared minus x times z is equal to 0. Right? X, big X equals little x. Yes, cool. So all I want this to do is, yeah, right. Do we start counting from I? Or start counting from 0? Do we make an array? Do we have to initialize it? Cannot assign to a function call. Should do Zach's code challenge. I need a lot of help before I get to that level. Because it has been years since I've done any like real coding. So I guess you all should know this, right? Do we want to make an array, or do we want to make like a list of I mean, we probably want an array because we want to be able to do math with it. In MATLAB, that's why I kind of went MATLAB at first, was that it should be a lot easier to you're just literally creating a matrix with these things in it. The issue that I would have then is that octave is ephemeral, and just sneezing in its direction does cause you to lose all of your work. I've probably already lost whatever I had done before because I hadn't signed in. Not like it's a big deal. NumPy array creation. Okay. A range, 1, zeros, etc. Okay. So actually, yeah. Save projects on GitHub. Yeah. It's possible. np.array. Okay. because we included 0, 0, 0, 0 as a possibility. Okay. Okay. We want this to be S. S of X, Y, Z. Not quite. Because it's not a single value, right? It's not. We want this to be a vector. Yeah, actually, we don't need it to be a 3D vector. We just need it to be a 2D vector with size 3. We need 3 columns. So that's this one. What? What are you doing? I don't know what I'm supposed to be doing there. Okay, what does zeros want? Default D type is float 64, so yeah, we're just we don't even want a floating point, we want an integer. Okay, so this is not going to be XYZ. This is going to be S of this thing is going to be Y and no. And S of this thing is going to be X. So what do we want that to be? This is okay. Is the problem that this is starting with 0? Nope. Great. I1 and I2. Still not it. I actually don't know what they're talking about here, so. Cannot assign to function call. That's not what the problem is. Okay. Okay, so okay, so Python doesn't know what I'm trying to do. Why is there another error with the thing? Is it the capital letter? We need to have it be lowercase. No, you still got a problem with it? Change position of Python array. Okay. So, okay. So, what's the problem with this thing? This is really bothering me, and I don't know why. I need to let that go. It's like it's having problems with me spelling stuff, but like extract.py for Python should be pretty obvious. Okay, so all right, S as a list is going to be equal to x, y, z. Then we want to stick that list on the end of it. It literally is just
I know just how the times have changed. Lately we've all been acting strange. Don't let this moment slip away. While you wait for a better
should be
day,
like
look
that.
around you.
Okay, so if it satisfies the equation, take xyz as a list, and then adjoin. No, what's the correct word for that? Concatenate. Or append was the word that I was actually looking for, but concatenate's an awesome one. Okay, so I don't want you to call any of these legitimate interest nonsense. This is one of the bad sites where you have to go through and manually click every single one, or unclick every single one, and then hit manage choices, rather than accept all. Ugh. Oh, Davis Sobel won the Pulitzer Prize and #1 best-selling author for The Elements of Marie Curie. Very nice. Davis Sobel's biography on Einstein and Galileo were interesting. I don't know that I have them here. I think they're both upstairs. But alright, so 1, 2, 3, 45, 4, 7, and 9, 6, 10 have appended list 1, 2, 3 vertically. Ugh. Axis equals 1 appends along columns, so 1, 2, 3. I would rather it go this way. Axis equals 0 then? Would that be horizontal? Terminal? No, not terminal. Python console. So S equals, let's just go 0, 0, 0. And P dot append. You don't have, yeah, of course you don't. Import MP as MP. Append, nope. Dot append S 1, 1, 1 as axis equals 0. Nope. Okay, let's see. This 1 should fail because it can't do it vertically. And do something stupid like axis 3, right? That's out of bounds. I want it to be axis 0, but add a new row. So that's probably not the one I want. P.concatenate. S, comma, 1, 1. Nope. Nope. Ah, there it is. np.r underscore. I never would have figured that one out. R underscore. Okay, something's wrong. S. Oh, okay. It's an array, so I can't do it that way. So if we do it that way. Ah, gross. No. No. But it didn't. Okay. If anybody else knows why, this would be helpful. But why? Add a row on a numpy array. Use numpy dot r underscore np dot insert np dot vstack or np dot append axis equals 0. Now I did append axis equals 0, and it did not put it underneath. It put it on the end. Did you call? Did I call for Penn Center to come and help me? Absolutely. This is gonna play havoc on everything that I just did. Yep, it's awesome. Let's see if I go like that. How about append? I used this function in, not that one, but I use this function in numpy, which is np.append of s comma new matrix or new vector axis equals 0, and it stuck it on the end appended, but I've got this thing in geeksforgeeks.org that says if we use numpy append, it should add it to the bottom. It says add it. It says append using an empty matrix first with 0 rows and 2 columns. It's an option. So I want it to take a 3 and then, a 1 by 3 matrix and then stick it on the bottom, and stick that on the bottom, and stick that on the bottom, and keep going from there. Did we hit the end of our music? Might have. I did not do it well. Oh no, it's just quiet. Okay. Yeah, I hit like add songs to playlist like 3 times, so it should have enough. 2 hours and 23 minutes. Yeah, it should be enough. S isn't a matrix, so we're appending vectors. Yes, so it's an array. So I'm trying to add an array to the bottom of an existing array. So when I started, right, this was I don't know if there's something else we can do with that, but yeah. Ads are going to start in about 2 minutes. So yeah, I'm trying to, you know what, let's go the way that they suggest here, which is we say that S equals np dot empty 0, 2. Oh, screw that. Come on. Cannot interpret 2 as a data type. Oh. That wasn't the correct. Yeah, okay. Fine. 0, 2, comma, int. There you go. So if we try S, it should just be empty. Right. Ow. 0, 3. Boo. Okay, so now we want to S equals P dot. All right, let's try the R underscore bit again. S comma 111. Oh, come on. I probably used it wrong again. That's fine. Yeah, I did. Okay. R requires square brackets. Oops. Square brackets. Check the type of S. Is it a list? They need to be explicitly an array. Okay. So as doing it as np, as in like numpy.empty, it appears to be coming up as an array. But yeah, there's ad break. So we'll be back in 3 minutes. Apologies everybody for not stopping at a time, but whatever. It'll be fine. We just gotta figure this stuff out. Hi YouTube, how you doing? Let's see. Okay. A mix of cases. Okay. So that seems to have done it. Zeros. Constructor empty. Shape. D-type. So yeah, actually let's make it empty. Zero in 3. So this would have been parentheses here. 0, 3, comma, empty has to be created with 2, and then int. Let's give it... Man, I don't know what the notes keep popping up as, because I don't know. np.empty, parentheses. Shape, in this case 03, comma, int. Parentheses 03, comma, int. So I don't know why this is here. It's like I'm doing it right according to whatever else we got in here. It's like whatever. I'm gonna get salty at this thing. So S is equal to... Are you serious? Is that it? Is that... I'm gonna be so salty. S equals np.v stack S again. Oh my god. Oh, I hate it. So salty. Okay, so stack, and then if I just wanted to, no. If I just wanted to, could I throw one in here? Oh, I definitely could. Okay. God damn it. Okay. Okay, so if this thing satisfies that, then we're going to okay. And then do we just literally cycle every possible X, Y, and Z? That would be awful. Again, O cubed time we're looking at. But what other ways can we do it? Okay, if we... if we just say, like, you know, let's calculate what the different ways we can move are, and then try to calculate which one gets us closer to 0. We'll do either a million calculations of x squared minus y squared plus z squared minus xz to determine whether it's equal to 0, or can we determine anything particularly useful? In theory, we might be able to use the gradient 2x minus 2y plus 2z minus, I mean, we can't quite, doesn't quite work. We need, right, okay, yeah, right. That's not how that works. Right, in terms of x would be 2x minus z, and see if that got us see if that ended up getting us like further away from a new 0 value. It's kind of gross still. Okay, so what I want this to do let's go over to let's go over to void space here. Capture window, Excalidraw. Okay. That is where I wanted it. Cool. Alright, so when we did this, we said that we're going to take all possible x, y's, and z's. So this is going from 0 up to 100, 1,000, whatever we feel like. Okay, so we have x squared minus y squared plus z squared minus xz equals 0 is our like objective function. Now we want to find all triplets in z cubed plus that, or z third dimensional space in the positive direction that satisfy the above objective function. So what would be the quickest way to cycle through all of the available locations in 3 space and calculate them all? Or at the very least, be able to eliminate a bunch and be like, this is not a 0 because I say so. Right, this would be 1 times 10 to the 6 calculations. Of objective. So if we end up doing the gradient of the objective, right, what is that going to get us? It's going to be a vector 2x minus z, negative 2y, and 2z minus x. Initially, I was just trying to, like, plot the objective function in 3 space in MATLAB. But that involves, like, making a color gradient and all sorts of other stuff. So, or now I'm just making a list of all the possible values, I guess. Like, I think it would be nice to have an actual visual, but we've gone down quite the rabbit hole here. It wasn't even what I was trying to do in the first place. Anyway. All right. This paper studies the density of prime triples and coprime triples in algebraic surfaces in C cubed. Okay, so complex space with 3 possible complex numbers. Clearly, the majority of such surfaces don't contain any non-zero integer triples. For instance, the surface z0 squared equals root 2 z1 z2, or z0 cubed plus z1 cubed equals z2 cubed, not mentioning prime triples. So to make the study meaningful, it is important to pick the right class of surfaces. This paper considers the surface, as above, which is the projective spectrum or eigensurface associated with an irreducible representation of the symmetric group S3. Although this surface is specific, the method used here could be generalized to work for some other algebraic surfaces. In the sequel, we review relevant concepts and state the main theorem of this paper. The notion of projective spectrum was introduced by the third author, R. Young. Let B be a unital Banakh algebra, and A be equal to A0, A1, etc., to a n be a tuple of elements in B. For z equals z0 through zn within complex n plus 1 space, we set A of z equal to linear. Nah, it's not linear. Banach algebraic combination of no, element-wise multiplication of A and Z. Projective spectrum of A is defined as P of A is Z within C n plus 1 space. A of Z is not invertible in B. Okay. Evidently, when B is a matrix algebra, the projective spectrum P of A is the algebraic variety determinant A of Z equals 0. In particular, the polynomial Q sub A of Z can be defined as the determinant of Z0I plus Z1A1 plus etc. ZNAN, called the joint or characteristic polynomial of the matrices. Zero variety, Z of Q sub A, is called the corresponding eigensurface. In the case where A1 through AN are representations of generating set of group G, it's known that the projective spectrum P of A captures some deep intrinsic properties of G and the representation. For example, for certain self-similar groups, such as the infinite dihedral group, the lamplighter group, and the Grigorchuk group of intermediate growth, the projective spectra of A are shown to be closely related to the Julia sets of spectral dynamic systems for the groups 5, 7, 19 found in references. In a different direction, maybe. Is that what that means? Yeah, citation. Okay, yep. In a different direction, the characteristic polynomials for finite-dimensional Lie algebras have also been actively studied, 239. For more details about developments, we refer the reader to the monograph 18 and references therein. This paper aims to initiate an investigation on the number of theoretic properties, which, by the way, this is the paper. Focus here is the symmetric group S sub 3, which is isomorphic to the dihedral group D sub 3, vector A of t defined where A squared equals T squared equals at cubed equals 1. Irreducible unitary representation of D3 is defined by the mapping row of A is equal to 0 e raised to the 2I over 3 e to the negative 2 pi I over 3, 0. And row of t is 0, 1, 0, 1. Characteristic polynomial for row of A, row of at is q of z equals determinant z sub 0 I plus z sub 1 row A plus z sub 2 row of at. It's equal to is equal to the one we're looking at right now. So, yeah. Corresponding eigensurface is what we're talking about. It is worth noting that not every finite group has an eigensurface containing prime tuples. For example, dihedral group 8, D8, for which the angle matrix row of A is above pi over 4 instead of 2 pi over 3. Hence, our choice of group S3 is not arbitrary. In fact, we have long speculated in surface S in 1.1 contains a higher density of prime triples compared to that of Z3+. Apparently, the symmetry of S plays a role here. Example, if Z0, Z1, Z2 is a prime triple in S, then so is Z2, Z1, Z0. Right. Symmetric. Indeed, numerical calculations confirm that among tens of millions of coprime triples in S intersect Z3+, the density of prime triples is greater than that for the set of Z3+, indicating S meets primes more frequently. It is an intriguing question whether this phenomenon holds asymptotically. We'll prove the answer is yes. Spoilers. No, that's what the abstract was for. First, we give a precise formulation of the problem. Let number x denote the number of elements in the finite set X. For positive integer n, we set pi of n equal to number p less than equal to n, where p is prime. Prime number theorem in reference 8, theorem 6, states that pi of n is equal to n over log n times 1 plus O of 1 when n is large, showing that density of primes in the set 1 through n is asymptotically equal to 1 over log of n. Simple calculation verifies that if z is a prime triple in S, then z0, z1, z2 is not equal to 0. Hence, we assume no coordinate of z is 0. And to find that, d plus of n is equal to the following. Okay, so z0 needs to be between 1 and 6/5 n. And n is large. For some positive integer n. Right. The prime we're looking for is less than or equal to that particular value. So z0 and z2, what I have termed x and z in the program, must be less than or equal to 6/5 n, whatever large value we're using. So if I've selected 100 as the, limit value, then our large number n is going to be 5/6 of that. Which is not very big, so it's like 80 something. Okay. And then z1 must be between y must be between 0 and n. Okay. Done that way because we're subtracting the middle number. We're also subtracting x and z. The fact that d plus of n is cuboid rather than an actual cube will offer convenience for subsequent study. Nice. Define x plus of n equal to z within d plus of n. Z is a prime triple. Y plus of n is equal to z belonging to d plus of n is a coprime triple. Set p plus of n equal to number of x plus in n of n over number of y plus of n. Intuitively speaking, the ratio p plus of n is the density of prime triples in the set of coprime triples in Z3 plus bounded by n. In section 2, we give an estimate of p plus of n. This serves as a basis for the subsequent comparison. For the eigensurface S in 1.1, we define, right, S plus of n is equal to S intersect x plus of n. Fair enough. Similarly, set PS plus of n equal to the following. Density of prime triples in the set coprime triples. It's worth noting that the estimation of number ys plus of n is the key to the whole problem. Let zeta denote the Riemann zeta function. Following is the main theorem of the paper. Following hold for eigensurface S in the group S3. Limit of infimum of PS plus of n over p plus of n is greater than or equal to the following values, which is approximately 1.0002, and the limit of the supremum of PS plus of n over p plus of n is less than or equal to that stuff, which is approximately 1.0534. It's worth mentioning that in the process of proving this theorem, we'll establish several facts of independent interest in number theory. Since the paper concerns the density of prime triples in Z3 plus and S intersect Z3 plus, the results presented here can be viewed as higher dimensional generalizations of the prime number theorem. Whew. Right, so let's go back to the prime number theorem. 8. G.H. Hardy, An Introduction to the Theory of Numbers. That wouldn't happen to be the book I have, is it? Somehow I don't think so, but worth a look. Nope, not that one. Hardy. It's here somewhere. Oof. Alright, let's see. Oh, is that one it? Course of Pure Mathematics. So that is not the one we're looking for. So that is the theory of numbers specifically. Ow. we could just look it up, so. Prime number theorem. Right, so it's just that. N over log of n. That was not what this one says. N over log of n times 1 plus O of 1. Approximately equal to, right, okay. Yeah, there we go. That one's using complex analysis. Yep. Right. So it's just the essentially remainder amount. Section gives an estimate of p plus of n. First we recall some terminologies and notations which will be used in the sequel. Given two real functions f and g, with g non-vanishing, we write f approximate g. Now, f is of the same order of g if, as x goes to infinity, the limit of the ratio of f and g is 1. For g non-negative, notation f equals O of g means there is a constant c, non-zero, positive, such that, okay, absolute value of f is going to be less than or equal to c g of x for any given r, a real number, for where x is real numbers. Moreover, if we write f equals lowercase o of g in the case of limit as x approaches infinity, f over g is equal to 0, the symbols floor dot and ceiling dot denote floor function, ceiling function respectively. Yeah, okay. Mobius function mu z plus mapped onto 0 plus or minus 1 is defined by the following. Mu of d is equal to 1 if d is 1, negative 1 to the k if d is a product of k distinct prime numbers, and 0 if d has one or more repeated prime factors. Okay, interesting. Nyman shows that k positive integers chosen at random from the set are relatively prime along with the probability. For k greater than or equal to 3, probability, these things, where zeta is the Riemann zeta function, 1 over zeta of 2 plus big O of log n over n for k equals 2. density of prime triples and co-prime triples is the following. Theorem. Estimate number y plus of n, number x plus of n separately. Total number of triples is this. Number of triples with all three elements composite is the following. Thus, the number of triples with at least one prime is the following. We subtract the number of triples which are not relatively prime. This occurs only if one of those is prime and the other two are integer multiples. The number of such triples is given as the following. Little o of n cubed over log n. Therefore, number of x plus of n is equal to the following, and it follows that p plus of n is the following. Okay. Okay, so we've got this amount here, this amount here. We're taking that, we're dividing it by, nope, dividing it into this amount up here. Okay, give an estimate of number x s plus of n, where we recall that the following is, right, x s plus of n is z belonging to surface intersect d plus, which is our the surface that was going to hold all of our prime dihedral group. The intersection of the surface plus the dihedral group at n is going to be defined where z is a prime triple. Okay, so we get number x s plus of n is equal to 2n over log n plus little o of n over log n. In order to prove this, we need to parameterize the eigensurface. Recall S is determined by the Diophantine equation. Anybody who's new here, welcome. My name's Obi-Wan Pez, and this is N Simple X Pachinko. We're doing, well, we're reading some mathy stuff. This one's on the arXiv. It is all about, actually, it's the last chat message that's just over there. This one is all about trying to find the density of prime numbers in a generalized 3 space. This one specifically is looking at the symmetric group S3 and the eigensurface of that symmetric group. So they were like, okay, well, we're going to use this particular surface because there's a whole bunch of other I mean, there's literally an infinite number of surfaces you could use. But they decided to use this one because it specifically talks about the density of prime triples. And that surface meets primes more frequently. So they were like, this is a more interesting thing that we could use other than just talking about other various surfaces that they could, in theory, have. There's a good one in here. Yeah, projective spectrum. If I'm honest, right, I don't really know a whole lot about it, but irreducible unitary representation of D3 is defined by the given map here, and that then produces, when we look at the characteristic polynomial for rho of AT, it gives us the characteristic polynomial, which is the surface that they're looking for, or the equation of the surface that they're looking for. The expression of one side. And then when they set it equal to 0, that's the eigensurface. And they were like, let's do that. Right. So, S is determined by the Diophantine equation. I shorten this to x squared minus y squared plus z squared minus xz equals 0. It's fine. It works. Rewrite equation 3.1 as the following. So make z1 squared positive, move it to the other side, and we get z0 squared plus z2 squared minus z0 z2. And then they said that cosine of pi over 3 is a half times 2 gets us 1. So we could just have this as an equivalent equation to this, because all we're really doing is multiplying by 2 and dividing by 2. The form which we choose is a little bit different, but that's an interesting representation for it because this is the law of cosines. So by the law of cosines, a positive integer solution of equation 3.2 corresponds to the integer-sided triangle of a pi over 3 angle. So this is a 30, 60, 90 triangle that they're producing, whose opposite side is z1. If z0 equals z2, then z0 equals z1 equals z2. If z0 equals does not equal z2, Gilder proved, reference 4, following fact about the non-equilateral integer-sided triangles with pi over 3 angle. Non-equilateral integer-sided triangle has an angle of pi over 3 if and only if it is similar to precisely one member of the class of triangles whose sides are m squared plus mn plus n squared, m squared plus 2mn, and either n squared plus 2mn or m squared minus n squared, where m and n are positive coprime integers, m being greater than n and not equivalent to n mod 3. Interesting. So I assume that comes from the study of Pythagorean triples and right, pattern. Yeah, this stuff. triple generated by Euclid's formula is primitive if and only if m and n are coprime and exactly one of them is even. When both m and n are odd, then a, b, and c will be even. The triple will not be primitive. Makes sense, right? You'll always be able to just divide by 2 to get the primitive of that. Despite generating all primitive triples, Euclid's formula does not produce all triples. For example, 9, 12, 15 cannot be generated using integer mn. Well, yeah, that's not a primitive. Wait, what? Nine, 12, 15 isn't a primitive, so why are we even talking about it? Doesn't need to be. Oh, does not produce all triples. Yeah, okay. No. That makes sense. Jeez. Whew. Okay. Citation needed. Nice. Anyway. For each triangle in the class, greatest common divisor of the three sides is 1. Works for me. Okay, so yeah, we're looking at a Pythagorean primitive for that. That's fair enough. Lemma 3.2 offers parameterization of coprime solutions of equation 3.1. Omega is equal to mn belonging to z2 plus, defined where the GCD of m and n is 1, m is greater than n, and m is not n mod 3. Define the following 4 maps. Phi1 is mapping z2 plus onto z3 plus. M and n, I forget what that arrow is, being mapped. Okay. Mn is being mapped onto m squared plus 2mn, m squared plus mn plus n squared plus 2mn. Okay. Phi 2. Same definition, but mn is being mapped onto n squared plus 2mn, comma, m squared plus mn plus n squared, and m squared plus 2mn. Phi 3, okay, so these are just different combinations of the exact same thing. I have to go over here. Really? Sync now. I swear, my clock does not like being synced. There's a good chance that the battery over on my other computer desperately needs some syncing. Sorry, the battery on the motherboard probably needs to be replaced. This happened once before, a very long time ago, or at least something similar happened a very long time ago. Okay, feed 3, m squared plus 2mn, and m squared plus mn plus n squared, and m squared minus n squared. Right, we discussed that before. So either this one could be m squared minus n squared, or n squared plus 2mn, I think was the... yeah, n squared plus 2mn, or m squared minus n squared. So here we see it again with this one, 2 and 4. And 1 and 3 replaced Z with that stuff. Easy to verify, all 4 maps are injective. M greater than n implies that the ranges of those maps are pairwise disjoint. Hence we have the following lemma. 3.3, given any Z in Z3 plus with GCD of Z equal 1, it is a solution of the equation 3.1 if and only if it belongs to one of the 5 disjoint sets given here. Delta 0 equals 1, 1, 1. Delta 1 is equal to phi1 of mn, defined where m and n are on omega within the set we talked about up here. So GCD of m and n are 1, m is greater than n, and m is not equivalent to n mod 3. Delta 2, same thing but for phi 2. Delta 3, same thing but for phi 3. And delta 4, same thing but for phi 4. Cool. Because again, they are disjoint. Thus, counting x s plus of n amounts to computing the number of prime triples in each delta sub I intersect with dihedral group plus of n. Observe that symmetry of S in Z0 and Z2 implies number of delta 1 intersect dihedral group of n is equal to number of delta 2 intersect dihedral group of n, while delta 3, same thing, is equal to number delta 4 intersect dihedral of n. Next limit justifies using the cuboid d plus of n instead of a cube. So that could be something that is used for efficiency for the for like the values that I was using. We could, in theory, find some way to eliminate a bunch of x's, y's, and z's based on the dihedral group rather than using the cube x, y, and z from 0 to 100 or 0 to whatever our maximum is. I was using 0 to 100 because I figured it'd be an easy-ish way to do it. It does imply, though, that means we need to do a million calculations of the surface in order to figure out what triples are zeros of the surface. Zeros on this, whatever. Ads are starting, so we're going to go do that. I'm going to actually get up and take a break here. So see you all in 3 minutes. Be right back. Thank you so much for coming, and we shall return. How's everybody doing tonight? Let's just might as well friggin' do it. All right. Hope you all are in for a... Yeah, everybody's in for a treat here. I hate push-ups. Like that or something. In addition to the fact that I just can't do them properly. Arms are weak. So we can do 10, super easy. I can usually do about 15 just straight. The holiday weight is unfortunate. Holiday weight is real. Hate push-ups. I have always hated push-ups. Doesn't help I'm no good at them. 20 has like been my hard limit for my entire life. I hate it. But then again, I did just bring up the last of the holiday brews. This one is hashtag not sponsored. Yeah, it's looking good. You all can see it. Outland West Coast IPA from Badger Brewery. Oh good, my other computer reached a 3-stream streak. I don't know how that's possible given that it is here every single day. Okay. Yes, I don't know how I could possibly have holiday weight. Oh. Everybody sent us all the candy. Friggin' A. Okay. So given all that again, justifies the use of cuboid instead of the cube. For the deltas, for any z in those triplet sets, it holds that z is going to belong to the cuboid if and only if z1 is less than or equal to n. So that was our... n is the big number that we're using to find our prime triplets. It's kind of our, like, high-end limit value. When are we stopping? When are we stopping looking for zeros of this particular service? So, it suffices to prove the sufficiency. One would hope. We'll show that for any z in delta 1, when z is less than or equal to n, we have z belonging to dihedral group of n. Proofs for all of the delta I are going to be similar. So for any z in delta 1, we have z0 equal to m squared plus 2mn, z1 is equal to m squared plus mn plus n squared, z2 is equal to z squared plus 2mn for some mn in the omega group. Right, the mn that we're using to, like, justify this whole thing. Note that m is greater than n, so if z1 is less than or equal to n, we easily get that z2 is less than z1 is less than or equal to n is less than 6/5 n. Okay. So z2 being less than z1 is a factor of how we define things above. z1 being less than or equal to n is how we defined what z sub 1 is going to be in the last line, right here. And 6/5 n is less than or is greater than n is given. So therefore, z0 over z1 is equal to that stuff over that stuff. Make m over n in all of the places that we can. And as m over n What is happening to m over n? Is m over n going to 0? No, because that would just be 2. Ah, those are the sides of the 30, 60, 90 triangle that we're using to justify all this stuff. So z0 is going to be the one side that we're working with, and root 3 is going to be the vertical side. I think so. And Z2 was going to be the half side underneath. Anyway, 2 over root 3 is less than 6/5. So therefore, z0 is less than 6/5, z1 is less than or equal to 6/5 n, showing that z must be a member of that dihedral group. Okay, so we can use, instead of having a literal cube of values, we could start cutting into some of those things and have it be cuboid. It's going to also eliminate a bunch of stuff where y is a particularly high value, I think. And if z0 or z2 are x or z when we were doing this, are disparate from each other, so particularly separated, then x squared plus z squared minus xz is going to have a larger value. Our friends who lived across the road and have since moved back to the U.S. The wife had done for her husband, like during their first year or two of marriage, I think, made him a beer advent calendar. So she went and bought 25 different beers and like wrapped them all, or well, okay, 24, and wrapped them all up. I think it might have been 25. Wrapped them all up, and then like individually, one at a time, he went through the entire month and, you know, opened one a day, and it was like, oh, this is really cool. And they started, I think she found like 5 other people who would be interested, and so they all went in together, bought 6 packs of everything, and then broke them all up on a certain day, wrapped them all up, and then gave them to their spouses, whoever is the interested beer person in the family. I got into that multiple years in, and so they were looking for like a, I want to say 12th couple, when my spouse was like, yeah, we'll do that. Didn't tell me about it, and then showed up on day 1 with number 1 wrapped up, and I was like, what are you doing? She's like, it's a beer advent calendar. I'm kind of missing that right now, but at the same time, like, that level and requirement of time and organization is something that I just do not have right now. She also did, like, try to get as many seasonal beers as possible, rather than flagships. Okay. 2 other functions are needed to prove Theorem 3.1. First is the function pi of n qa, which is going to be defined as the number of p less than or equal to n such that p is prime. P is equivalent to a mod q, which counts the number of primes p equivalent to a mod q up to n. And the second is Euler's totient function. It's also a phi, right? Phi of q, which counts how many numbers from 1 to q are relatively prime to q itself. Landau's theorem gives an estimate. Let a and q be greater than 0, relatively prime integers, then p is equal to 1 over phi of q times n over log n times 1 plus O of 1. Since phi of 6 is equal to 2, asymptotically we have p of n 6 1 is equal to p of n 6 5, which is equal to n over 2 log n of 1 plus O of 1, which is half the number of primes up to n. We're now ready to prove Theorem 3.1. Boy. Recall that the set X, S plus of n consists of prime triples Z in the surface intersection with dihedral group N. Obviously the set delta 0 does not contain such triples because delta 0 is just 1, 1, 1. Thus, in view of lemma 3.3 and Theorem 3.3 and equation 3.3, jeez, it suffices to count such triples in each delta I intersect dihedral group of N, where I is 1 and 3. Okay. For Z in delta 1 intersect dihedral group N, since Z0 is equal to m squared plus 2mn cannot be prime, we consider the two subsets of delta 1. Let delta 1, 1 be equal to Z in delta 1 such that Z1 is prime. Delta 2, 1 equal to Z in delta 1 such that Z2 is prime. We will count delta 1, 1 intersect dihedral N and delta 2, 1 intersect dihedral N separately. For Z in delta 1, 1, lemma 3.4 includes that Z in delta 1, 1 intersect dihedral group N if and only if Z1 is less than or equal to N. I think we're good for that anyway. Since Z1 is equal to m squared plus mn plus n squared, we need to count the number of coprime pairs mn in omega such that m squared plus mn plus n squared is prime not exceeding n. Nair 13 proved that for each prime p equals that, corresponding coprime pair mn with m greater than n is unique, and hence corresponds to a point in delta 1, 1. Further, Calder 4 observed that a prime p is not 3 is of the form m squared plus mn plus n squared for some coprime pair m and n if and only if p is equal to 6k plus 1 for some k in z plus. That is, I'm pretty sure I've seen that proof, and it's pretty awesome. Calder. Calder proof coprime. Really? You jerks. Like, literally the density of primes paper that we're reading right now. Ew. Lemma 3.5 indicates that the number of delta 1, 1 intersecting with dihedral group of n is going to be equal to 1/2 n over log n of 1 plus O of 1. For z in delta 2, 1, z2 is equal to n squared plus 2mn can be prime. It can be prime only if n equals 1. Hence, number of delta 2, 1 intersect dihedral of n is less than or equal to the number of phi1, m1 in dihedral of n defined such that m, 1 is in omega. Since, hang in there, phi1 of m1 is equal to m squared plus 2m, m squared plus m plus 1, 2m plus 1, by lemma 3.4, phi1 of m1 must belong to dihedral of n if and only if m squared plus m plus 1 is less than or equal to n. And that means that m is less than or equal to, using the quadratic formula, I'm guessing bringing the n to the other side. Let's see. This is going to be negative b is negative 1. Yeah. Plus or minus. And in this case, we're using the plus square root of b squared, which is 1. Minus 4. A is 1. C is 1 minus n. Right. So 4 times 1 minus n. Hang on a second. Wait a second. Minus n less than or equal to 0. Right, this is going like that, so clearly it's... Oops, nope, not doing that. Not doing that either. Shifted to the negative side slightly. It's gonna be like that. In theory. Right, could be on this side, but we don't know. Most likely not, because this should have a positive m as a right, m should be greater than 0, hopefully. Right, so this is m is going to be equal to, quote unquote, because we're doing, yeah, totally it's equal to, and then we figure out what the values are going to be, then make this work. So it's going to be between 0 and whatever this other value is. So actually, right? Less than or equal to. I think we don't want m to be 0. So otherwise that could ruin stuff. Alright, negative b plus or minus square root b squared minus 4. A is 1. C is 1 minus n. Ah, right. Minus, minus. Right, we're good. I don't know why I was worried. So m is going to be between 0 and negative 1 plus or minus square root negative 4 plus 1 is going to be negative 3. And then negative 4 times negative n is going to be a positive 4n all over 2. Right. And then 4n minus 3 is going to be a large number because n is going to be like, you know, the maximum value that we're looking at or something like that. So we're going to say that this is probably going to be greater than positive 1. Sure. In order to make this whole thing greater than 0, if it is negative, then we've ruined everything, right? Then the negative is going to cause problems because that'll make the whole thing negative. And like we already said here, we want this to be positive. So never mind about the negative version here. So negative 1 plus square root of 4n minus 3 all over 2. And the way that they wrote it in the paper is not very high school friendly, but it's perfectly fine for everybody else, is the square root of 4n minus 3 minus 1 all over 2. Right there. Right, m must be less than or equal to that stuff. Therefore, number of delta 2, 1 intersect with the dihedral group of n is less than or equal to the floor function of the square root of 4n minus 3 is equal to O of n over log n. Okay. Oh. Yes, that's fine. Yeah. We're using floor function here to mitigate some of the error issues. Consequently, number of delta 1, 1 intersect delta 2, 1 intersect dihedral group of n must be less than or equal to the number of delta 2, 1 intersect dihedral of n must be less than or equal to... Right, yeah. Right. Okay, that makes sense. The number of intersections you have starts paring down more and more stuff. So, by definition of intersection, right, the intersection of delta 1, 1 with the other stuff that we had must have the same number of elements or fewer if we have paired any off. P-A-R-E-D, paired. Must be less than O of, less than or equal to O of n over log n. Okay. Right, because that's just this line, right? It's this line right here that we're then taking the first and last elements of, placing them here, and then saying that this other stuff has to be smaller than or equal to the other stuff we already had. Hence, we have number delta 1 intersect dihedral of n is equal to number of delta 1, 1 intersect dihedral of n plus number of delta 2, 1 intersect dihedral of n minus number of their intersections with each other. Interesting. That's Venn diagram. Who knows what I'm talking about? Right, A, B, A intersect B. So the total is equal to the number of A plus the number of B minus the number of their intersection. Because when you count them and you just say how many are in A, you're counting all of this stuff that's in all of this. And then when you count B, you're counting all of the stuff that is in this. So this area here has been double counted. So therefore, we subtract off one of those intersections. Okay. That's pretty awesome. I hadn't even thought of it that way, but it makes complete sense. Which is equal to 1/2 n over log n of 1 plus O of 1. Estimation for delta 3 intersect dihedral of n is similar. In summary, we have number of x s plus of n is equal to 2n over log n plus O of n over log n, as claimed by Theorem 3.1. Ta-da! This section gives an estimate of number y s plus of n in the exact same way that the previous section was talking about number in x, right? Yep, number in x s plus of n. Yep, there. This is the critical step for establishing the main theorem. First, recall y s plus of n is equal to z equals, z is a member of S intersect our surface intersect the dihedral group of n such that the GCD of z is 1. Following inequalities hold for y s plus of n. Okay, we've got some of that stuff up there. But this is the theorem, so don't take that at face value. Right. Like the case for x, counting y amounts to counting delta I intersect dihedral of n for each I equals 1, 3, and sufficient to do so just for I equals 1. Again, the issue is that I3 is going to potentially end up with there was something. Damn. Right here. Suffices to count triples in each. I equals 1, 3. Have two subsets. Estimation for delta 3 is similar, right? And we end up with what ends up being, this particular setup here. Right, this is not the value we're looking for. It leads us to that particular value. Okay. Sufficient to do so just for I equals 1, and then figure out what's going on. So for m, oh man, we're like halfway through the paper. Realistically, there should be a lot of references. For m being positive, k1 being positive, k1 being greater than k2, let t of m, k1, k2 be the triangular region within the first quadrant of the plane enclosed by the m-axis. Lines L1, L2 are defined such that L1 has m equals k1n, and L2 is m equals k2n plus m, shown by figure 1. So here we're seeing that both are going to intersect at the origin, come up to a particular point, and then L2 is going to have a horizontal. Okay, is going to have a horizontal 0 at m comma 0. Okay. M equals, okay. Because they're setting it up backwards from the way we usually do stuff. This is essentially x equals instead of y equals. Define C of m, k1, k2. This is easy algebra. Nice. Is equal to the number of mn in the triangle, where GCD of m and n is 1. C hat is defined as same thing, but GCD of mn is 1 and m is not n mod 3. We estimate C and C hat below, Estimation of the latter is subtle, but key step to computation. So we do the following. So here we got L3, which is cutting into L2. And it's going to eliminate the lower region, I suspect. We'll talk about that in a second. Both setup have the intersection point given here. K1m over K1 minus K2, comma, m over K1 minus K2. Where K2 is less than 0, we have the following. Right, K2 was the slope of L2. So we want the slope of L2 to be negative. Makes it a little bit easier to work with, I assume. The following hold asymptotically for a large m. C is going to be equal to 3 over pi squared times m squared over K1 minus K2 plus O of m squared. C hat is equal to 3/4 C plus O of m squared. Okay. In order to prove lemma 4.2, we need basic facts about the sums of Euler-Totient function phi of n, the function d of n, which counts the number of positive divisors of n, summarized as follows. For sufficiently large n, the following hold asymptotically. The sum of the number of totient function values, no, not quite. The sum of the totient values going from 1 to big N, which again is going to be a big number, and as we go to infinity, it is asymptotically stable, is equal to 3 over pi squared n squared plus big O of n log n. Secondly, the sum of totient over n, as we go from 1 to big N, is going to be equal to 6 over pi squared big N plus big O of log big N. And the sum of d of n, the number of positive divisors of whatever n value we have, the sum of the positive divisors of every n up to big N. It's going to be equal to big N log big N plus big O big N. Big O of big N. Okay. Given a positive integer n, let f of big N, comma n, denote the number of integers between 1 and big N that are relatively prime to n. Obviously, f of nn is Euler's totient function of n. Tolth shows that f of big N little n is equal to the sum of Mobius function mu of d times floor of big N over d. Of course. Oh. Which is going to be equal to where omega of n is the number of distinct prime factors of n. That f value is equal to totient of n over n times big N plus big O of 2 to the omega n, omega of n. Thus, in T, for a fixed n, the sum of m belonging to k1n, k2n plus m that are relatively prime to n is f of floor k2n plus big M, comma n, minus f of ceiling k1n, comma n, which is the totient of n over n times, right? This is just a simple substitution, although the terms are ridiculous. It makes complete sense, at the very least, that yes, if you have these things, you can replace one with the other. Of course, sure, that's fine. Oh, man. C can be the following. Doop-a-doop-a-doop. Lemma 4.3, C can be then that, which does include big O of the sum of 2 to the omega of n. Okay. Whee! Using a dummy variable h, which just kind of came out of nowhere, it's fine. I don't see an h. Nah, cool. I'm just gonna pop a dummy variable h in there for, you know, reasons. Substituting h equals, there we go, floor of big M over k1 minus k2 equals m over k1 minus k2 plus big O of 1. We have the following. C equals 3 over pi squared times big M squared over k1 minus k2 plus little o of m squared plus big O of all that stuff with h. Estimate big O for a given n, which is the which is the product of all individual primes raised to whatever power they might be. We have that omega of n is equal to k. D of n is equal to t1 plus 1, t2 plus 1, etc., multiplied out to tk plus 1. So it's a pi, big pi, product of t sub I plus 1 for all 1 to k. So all of the exponents, right? It's all of the exponents plus 1 multiplied together. Since 2 is less than or equal to t sub I plus 1 for each I, assuming that... Well, hang on a sec. Oh, yeah, right. P1 through PK are distinct primes from each other, but they are the prime factors of n. So we're not including, 2 for any odd, 2 to the 0 for any odd numbers. I guess in theory you could say that, like, some odd number is going to have a 2 raised to the 0, so that particular term would end up being 0 plus 1, so it's 1. Like, sure, you could include all primes before that particular number. It doesn't matter. But yes, for simplicity's sake, P1 through PK can just be the primes that we're going to use. Since 2 is less than or equal to t sub I plus 1, we have that 2 to the omega of n is less than or equal to d of n, hence by Lemma 4.3. The sum of all 2 to the omega of n is less than or equal to the sum of d of n, which is then going to be equal to h log h plus big O of h. Okay? Set C prime equal to the number of mn within the triangle, such that the GCD is 1 and m and n, m is equivalent to n mod 3. And we can show that C prime is equal to 1/4 C plus little o of m squared. Claim in 4.2 immediately follows. Okay. Count the number of coprime pairs in T satisfying the conditions above. Let n be fixed. M belong to K1n, K2n plus m. Since m is equivalent to n mod 3, we can write m is equal to n plus 3t, where t is an integer belonging to k1 minus 1 times n all over 3, comma, k2 minus 1 times n plus m all over 3. Due to the fact that the GCD of mn is equal to the GCD of n plus 3t n, GCD of 3t n, the number of coprime pairs is equal to that of t in the given interval, for which GCD of 3t and n is 1. Note that GCD of 3t and n is 1 if and only if 3 does not divide n, and GCD of tn equals 1. Okay. Hence, C prime is equal to the number of coprime pairs Tn satisfying n belonging to 1 to h, 3 does not divide n, and t is in the interval discussed. Thus, C prime is equal to the sum of the totient over n, difference between x and y values. Not really. It's floor of one, ceiling of the other. Plus big O of the sum of all 2 to the omega of n's, by the same reasoning that we have in part 1. Stuff. The sums need to be estimated separately. Good times. Obviously. The sum of all n's going from 1 to h, as long as 3 is not divisible, or n is not divisible by 3 of the totient, is equal to the sum of the totient minus the sum of the totient where n is divisible by 3. That makes sense, right? You're just cutting out individual ones. In fact, it's every third that you're just cutting out here. So, sure. Estimate of phi of n follows from 4.3, so it remains to estimate that phi of n3. The estimation procedure follows Lemma's computation in 11, lemma 2. First, for j belonging to z+, we will provide phi of 3j is equal to either 2 totient, not phi. Totient of 3j is equal to 2 totient of j if 3 is not a factor of j, or 3 totient j if 3 is a factor of j. Boy. Not hard to see that if GCD citation needed. GCD AB equals 1, then totient AB is going to be equal to the product of the totents of AB. That's pretty nice. Hence, if 3 is not a factor of j, then totient of 3j is going to be equal to the totient of 3 times the totient of j, which equals 2 totient of j. Okay. If 3 is a factor of j, there exist q and t in z plus, such that j is equal to 3 to the cube t, and GCD of 3t equals 1. Observe that totient of 3 to the cube plus 1 is equal to 3 to the q plus 1 minus 3 to the q, and consequently we have totient of 3j is equal to totient of 3 to the q plus 1 times t, which is equal to totient of 3 to the q plus 1 times totient of t, which is equal to 3 to the q plus 1 minus 3 to the q times the totient of t. Similarly, totient of j is equal to totient of 3 to the q plus times t, which equals 3 to the q minus 3 to the q minus 1 times the totient of t. So therefore, totient of 3t, nope, totient of 3j is equal to 3 totient of j. Woo! Similarly, we have totient of j. No, we just did that. Literally. Proves equation 4.2. Establish the following iterative formula. For n and z plus, it holds that phi of n3 is equal to 2 phi of floor n over 3 plus phi of floor n over 3, comma 3. In fact, since phi of n3 is equal to the following sums, by equation 4.2, we have nope, that's a phi. Phi of n3 is equal to twice the sum of the totents of j, where j is going from 1 to the floor of n over 3 as long as j is not a multiple of 3, plus 3 times the sum of the totents of j when j is going from 1 to the floor of n over 3, where 3 is a factor of j. Goodness. So therefore, 2 times phi of floor n over 3 plus phi of floor n over 3, comma 3, is going to be our value that we get. Apply equation 4.3 repeatedly to estimate phi of h3. Note that for AB belonging to z plus, we have the following floor function. Follows that phi of h3 is equal to the following, etc., etc. Noting that the iterative process only has floor of log base 3 of h steps. Substituting lemma 4.3 into the above formula, we obtain phi of h3 is equal to 3 over 4 pi squared h squared plus little o of h squared. Consequently, the sum of all totents of n where 3 is not a factor going from 1 to h is going to be equal to phi of h minus phi of h comma 3, which is equal to 9 over 4 pi squared times h squared plus little o of h squared. Estimate the sum. Yep. Estimate phi 1 of h3 follows that the following is true. Substituting lemma 4.3, we got the following. Therefore, c prime is equal to all this stuff. Consequently, c prime is equal to 1/4 c plus little o of m squared, giving the desired result. Whoa. 4.2 could be generalized for the following situation. Let that T triangle be the triangular region within the first quadrant of the plane, enclosed by L1, L2, and L3. Let the number of coprime pairs be this stuff. Estimates hold. Remark here, the area of the triangle T is the following. Lemma 4.2 can be rewritten as the following. Corollary 4.4 can also be written as the following. Density of coprime pairs in the reasonable planar region is approximately 1 over zeta of 2 equals 6 over pi squared. Another corollary. Split E of n into multiple parts where the curve C1 can be approximated by different lines. Choose 3 straight lines tangent to C1. Okay, so tangent. Let ABCD denote intersection of L0, L1, L1 and L2, L2 and L3, and L3 and the M axis respectively. Get the following relationships, or the following points. Triangular region OAD contained within E of n, and E of n is contained in the pentagonal region OABCD, enclosed by L0, L1, L2, L3, and the M axis. And then get the areas of all the following pieces. Conclusions. In light of Theorem 3.1 and 4.1, we have the following. Theorem 3.2, we have the following. We have this, which is the following, establishing the main theorem of the paper. So we get the infimum and supremum of these two values, which end up getting us these values, establishing, main theorem. Oh. We leave further discussions for another paper. Very nice. All right. It's pretty close to 1, so we'll just snooze this. And we are going to come back tomorrow with, I don't think probably the finale, because I'm not good enough yet. All we need to do is get good, of 9 souls. So we're gonna get close, and then I think we want to figure out if we can find like the last 1 or 2 things that we're missing. So we're going to head over and see Dirensha, who is doing some work with lean and working on the nopertedron Lemma 33. So if anybody is interested, come on over, say hi to Dirensha, and we will see you all tomorrow for 9 souls. I will be back on Wednesday for more mathy stuff. We're going to be working on calculations of the GRE kind, and we'll be seeing how all of that works. So we'll figure out what new calculations need to be done. So I hope to see you all then. Good luck. Come back tomorrow if you want to see games. And for now, right, I didn't show you. We got a huge box of Lint Linders from my brother-in-law. Tiramisu, which is a new one for me. The usual white, dark, and milk. This one is cookies and cream, and there's like, I don't know, 16 possible flavors or something like that. We got most of them in there, so cool stuff. I need to do some working out. So, see you all tomorrow. My name's Obi-Wan Pez. This is N-Simplex Pachinko, and we'll catch you next time. Good night.